Hey folks, I've been rewriting all the exams so that every single exam problem is exactly like problems that you see on the homework. So to help you prepare for the exams, I'm going to go through how to set up various problems from your problem sets. And so this comes from the first problem set, and this is question number 9. And so we essentially have two people that are driving from Los Angeles to San Francisco. And in both cases, since they're going the same distance, we say the change in x is equal to the distance between Los Angeles and San Francisco, which is approximated to be 400 miles in this problem. So we have Alan, and we're told that Alan is driving a steady 47.0 miles per hour. And here's the key. Steady means that the velocity is not changing, which is to say the change in velocity over the change in time is equal to 0. You could go even more specifically and you could say dv dt, that's the instantaneous time rate of change of velocity, is also equal to 0. Okay, in both cases, this would be the average velocity, and this would be the instantaneous velocity. I'll just abbreviate instant for short. But the key here is that since we are not having a change in velocity, if we have any kinematic equations that have acceleration in it, those terms are going to vanish because the acceleration is equal to 0. And so we do indeed have the ability to say that some change in x, some displacement, would be equal to the velocity that is steady, okay? And if it's steady, then we can actually just multiply it by the total time interval. And so the total time interval is the time it takes to get from Los Angeles to San Francisco. And that's going to differ based on the velocity. And so we are told that Alan, so I'm going to say VA for Alan, is traveling at 47.0 mph. And we are told that we have Beth. And Beth is traveling at a steady 58.0 miles per hour. So Beth is traveling with a greater velocity than Alan, which is to say we know it's going to take less time for Beth to make the trip than for Alan. But we need to calculate how much. And then we're also going to have to keep into account the fact that Alan left Los Angeles at 8 a.m. and Beth left Los Angeles at 9 a.m. So there's a 1 hour head start that Alan gets. So let's see how much time elapses for each trip. So going back to this relationship where the displacement is equal to the steady velocity multiplied by the total time elapsed, I can divide both sides by that steady velocity such that the delta t is equal to the delta x divided by the steady velocity. And so I can write this for both Alan, so that's delta t Alan is equal to delta x. And the delta x, remember, is the same in both cases. It's 400 miles. It's the same start point, Los Angeles, the same finish point, San Francisco. And I can say delta x divided by VA, that's V Alan. And similarly, I can say that the change in time, the trip time for Betty, or Beth I should say, is equal to delta x again divided by V Beth. All right. So in both of these cases, delta x is 400 miles. And we know that Alan's velocity is 47.0 miles per hour. A lot of people are going to be honking at Alan because that's pretty slow certainly for an interstate. And similarly for Beth, it's 400 miles in the numerator. In the denominator, though, Beth is traveling at 58 miles per hour. In this day and age, that's also fairly slow for the interstate. And so, essentially, the wait time is going to be the difference in time between the person that gets to San Francisco first and the person that gets to San Francisco second, but then also to account for the fact that Alan got a 1 hour head start. I want to also incorporate how we can do some unit conversions. And so I'm going to show you how we can take miles per hour and we can actually turn this into minutes. And you can imagine you could be asked to solve this problem with different units, but I just want to give one example for how you do the conversion. So we're sticking, this is still problem 9. But what I want to do now is I want to convert the velocities, the times for both Alan and for Beth. So we have 400 miles divided by 47 miles per hour. Let's go back there, 47.0 miles per hour. The miles are going to cancel, and I'm going to get, because I have 1 over hour in the denominator, 1 divided by 1 over something is that something. So it's going to be 400 divided by 47.0, and that's hours. And I want to show you how you can convert this to minutes. Before we go any further, I'm going to take out my calculator. I'm going to go 400 divided by 47. 400 divided by 47 is approximately 8.51 if I'm taking it out to 2 decimal places. So this is approximately 8.51 hours. Now, what I can do is if I want to convert to say minutes, then I'm going to have to multiply this by something where there's hours in the denominator, so the hours cancel out, and we have meters still upstairs. And so this is sometimes called the factor label method, where you take the original quantity with its unit, and then you make columns that are different equivalents with units. And then what you do is you essentially multiply all the columns. And so I know that 1 hour is equal to 60 minutes. And so you see here how the hours cancel out. And so if I multiply by both columns, I'm now going to be in units of minutes. And so if I take 8.51 and multiply it by 60 minutes, it's going to be approximately 510.64 minutes. And again, this is for Alan. Alan takes 510.64 minutes approximately to go from Los Angeles to San Francisco. Now let's go back and let's look at Beth. 400 miles divided by 58 miles per hour. Miles cancel. We're in units of hours. So if I take 400 and divide it by 58, I'm going to get approximately 6.90 hours. And now I want to convert. So 1 hour is equal to 60 minutes. And so boom, boom. Now imagine if I wanted to go even further. Imagine if I wanted to go to seconds. I would have another column with the next column over. Minutes would be in the denominator, and then I'd have to know, well, how many minutes, correspond to seconds. And so I could have 1 minute in the denominator and 60 seconds in the numerator. So then I'd go 6.9 times 60 times 60, and that would give me seconds. Sticking to minutes, this is equal to 413.79 minutes. That's taking it out to 2 decimal places. So now I see, and I shouldn't be surprised because Beth is moving at a more rapid rate. It takes Beth less time. It only takes Beth 413.79 minutes to go from LA to San Francisco. And so the time difference, we'll call it TA minus delta TB. That's the time it took Alan minus the time that it took Beth. And that's going to be equal to 510.64 minutes minus 413.79 minutes. That's approximately 96.85 minutes, which is to say it took Alan 96.85 minutes longer to do the trip than it took Beth. Okay, but remember, Alan got a 1 hour head start. So 60 minutes into Alan's trip is when Beth starts. So that means in order to figure out how long Beth is waiting in San Francisco for Alan to show up, because she overtakes him eventually. She gets to San Francisco. It took him 96.85 more minutes. However, he started 60 minutes sooner. So the wait time for Beth, because Beth gets there first, equals 96.85 minutes minus the 60-minute head start that Alan got. Even with his 60-minute head start, he's still behind Beth by approximately 36.85 minutes. Okay, so just going back, we started out, we were given a distance, we were given a couple different velocities. We know that if the velocity is steady, that means that there's no change in acceleration, so we can say that the displacement is simply equal to whatever that steady velocity is multiplied by whatever time interval duration there is. We did a little algebra in order to rearrange things to express the trip time for both Alan and for Beth. I showed you how you could take that trip time, which was in units of hours, and convert it into minutes. And then I showed you how you could find the difference to figure out what's the total difference in trip time, but then we had to recalibrate for the fact that Alan got a 60-minute head start. And so that is how you work through problem 9. This is problem 12 from problem set 1. This is a problem where some calculus can really come in handy. So we're told that there's a particle, and that particle has some position as a function of time. So I'm going to call that x as a function of t. And we are told that this function of position, given the amount of time that we're interested in, is 5t cubed minus 9t squared plus 12. So if you can imagine a horizontal dimension, we'll call it x, and I say, what is the position x at time t equals 7? Then I have a function where I can input 7. You see every place you see t, you put it 7. 5 times 7 cubed minus 9 times 7 squared plus 12. And that number tells us exactly what the x-coordinate is at the time t equals 7. So that's why we can say it's x as a function of t. And so this is position. Now it turns out that if we take the derivative of x as a function of t, which is sometimes called x prime, so x prime of t is going to be the derivative of x as a function of t. And so the t to the cubed, the 3 is going to come down, multiply by the 5, and it's going to result in t squared. So I'm going to have 15 t squared minus, the squared term is going to multiply by 9, and then it's going to go to t to the first power, so it's going to be minus 18t. And the derivative of 12 as a function of t, there is no t there, and so the derivative of a constant is just going to be 0. So now it's just 15t squared minus 18t. And so it turns out x prime, which is the derivative of the position as a function of time, is also known as the velocity as a function of time. I can keep going. I can go x double prime. So this is the second derivative of x as a function of time. So now I'm just going to take the derivative of x prime to get x double prime. And so this is going to be 30t minus 18. And x double prime is often called the acceleration as a function of time. So we started with the position as a function of time, but we also could use calculus to figure out what would be the velocity as a function of time and what would be the acceleration as a function of time. For example, v as a function of time, if I was interested at t equals 3 seconds, then it would be 3 squared, which is 9 times 15, minus 8 times 3, and that would be the velocity at that specific time, t equals 3. If I was interested in the acceleration at t equals 5, then it would be 30 times 5 minus 18. That would be the acceleration precisely at t equals 5. So we are asked, at what time does the particle reach its minimum velocity? So you can think of it like this. Imagine that we've got some plot where we've got time on our x-axis and we've got velocity as a function of time on our y-axis. And so imagine that I'm going to plot what the velocity is at various different times. And so sometimes it could look like this, and sometimes it could say look like that. All right, you can see how it varies over time. But what I want to draw your attention to is here and here. The slope, if you look at velocity as a function of time versus time, the slope at both of those points is 0, which is to say the time rate of change of velocity with respect to time is 0, which is to say that the acceleration is equal to 0, both at that peak and at that valley. And so those peaks and valleys are essentially inflection points. So for instance, right here, dv dt would equal 0. If you think of the velocity versus time graph, the slope of that graph is going to, at a given point, is that instantaneous velocity divided by instantaneous time is going to be the acceleration, which is 0. And similarly right here, the slope at that specific point, which is dv dt, is also 0. But can you see how one is a maxima and one is a minima? So it turns out that when we have an expression for acceleration and we're interested at seeing when the acceleration is 0, we could end up having multiple solutions. We could have multiple points. And sometimes those points are peaks in velocity and sometimes they're valleys. This problem is asking us to solve for when the velocity is at a minimum. It wants us to solve for this point right here. That's a minimum. Can you see how the peak is at a higher velocity than at the minimum in that graph? And by the way, I just drew this green like hypothetically. That's not exactly what 5t cubed minus 9t squared plus 12 is, but I just want to keep it simple. When you have a function of something versus time, you're going to have fluctuations. You're going to have high and low values and values in between. Well, the maxima is the highest value, the minima is the lowest value. And so with respect to velocity versus time graphs, the slope of that graph is the acceleration. And so at peaks and at valleys, the acceleration is equal to 0. We know what the acceleration is because the acceleration is x double prime. So if I go back to the mathematics, I can say that 30t minus 18 equals 0. And again, that's because I'm interested in figuring out what is the minimum velocity and at what time does that happen. And that's at one of those points with the little red x's there where the acceleration is 0. That's what allowed me to say that this acceleration term right here can be equated to 0. So now I can do a little math. I can add 18 to both sides. So I can say 30t is equal to 18. Now I can divide both sides by 30, which says t equals 18 over 30. That can be simplified to 3 over 5. If you think 6 goes into 18 3 times and 6 goes into 35 times. And that can be simplified to 0.60 seconds. So t equals 0.60 seconds is going to be one of these maxima or minima. And I want to show you how you can determine if it's a maxima or minima. Because remember, when you're setting acceleration equal to 0, just as I showed you, you have multiple points. This is a point where acceleration equals 0. This is a point where acceleration equals 0. So this 0.60 seconds is a candidate for the time when the velocity is a minima. But we've got to make sure that it corresponds to this minima and not the other maxima on the left. So what we can do is called the second derivative test. And by the second derivative test, what I mean is that if I was to draw a line where I have 0.60 seconds, that's what we solved for a time where the acceleration is equal to 0. What I'm going to do is I'm going to think about what if I have a number slightly bigger than 0.6 seconds, and what if I have a number slightly less than 0.6 seconds? Going back to the acceleration, 30t minus 18. So let's go to the right of 6.6 seconds. So let's go 1 second. So if t equaled 1 second, you would have 30 minus 18 equals 12. And so that's positive. The acceleration at a time that is greater than 0.6 seconds has a positive value. Let's go less. Let's go, say, 0.5 seconds, which is the same thing as half of a second. And again, I'm going to go back to my acceleration equation, but I'm going to plug in now t equals 0.5. So 30 times 0.5 is 15. 15 minus 18 is minus 3. So you have negative here. So at 0.60 seconds, the acceleration, which is x double prime, is going from a negative to a positive. And so by going from a negative to a positive, we know that we are at a minima. If that was reversed, if it was positive on the left and negative on the right of 0.6, then we would know that we were at a maxima. But this has now allowed us to confirm the second derivative test, figuring out what t allows acceleration to be 0, and then testing terms for t just to the right and just to the left. It turns out that since we're going from negative and then to 0.6 seconds and then we're going to positive for acceleration, that means we have found ourselves a minima. This is indeed a minima. Another way of thinking about this is when the sign of x double prime, which is the acceleration in a velocity versus time graph, when it's negative, we can think of this part as concave down. Think of the minus as concave down. And we can think of over here as concave up. So when you go from concave down to concave up, you're at a minima. If you go from concave up to concave down, you're at a maxima. We definitely now know that this t equals 0.60 seconds is a minima in the velocity versus time graph. And so we have solved for this problem. The answer is indeed 0.6 seconds. That is when the velocity is at its minimum. And so we were also asked in part B of the problem. So everything I've been working on right now is part A. In part B of the problem, we're asked, what is V in the x direction's minimum? Well, remember x prime, that was this term right here, that can be expressed as V as a function of time. And so Vx min is quite simply x prime where t equals 0.60 seconds. And this equals 15 times 0.6 squared minus 18 times 0.6. This is equal to approximately 5.4. 18 times 0.06 is approximately 10.8, so minus 10.8, which equals minus 5.4 meters per second. So I knew that I had found a minima with the second derivative, which is the acceleration. I set the acceleration equal to 0, and then I did the second derivative test, just looking just to the left and just to the right of that 0. I saw that the acceleration term was negative just to the left, positive just to the right, and so that tells me, since I'm going from negative to positive, that I am at a minima. If I was going from left to right, if I had positive on the left and negative on the right, then I would be at a maxima. So I know that that corresponds to the minimum velocity. And so now I know the time is 0.6 seconds at that minima. I just plug that 0.6 seconds into my expression for the velocity, and that tells me what the minimum velocity is. And so the third part of the problem is actually redundant. It says, at what time is the acceleration 0? Well, I've already worked through that. The acceleration was set to 0 to get to 0.60 seconds to see if that was a maximum or minima. Once we determined it was a minima, so then the time that the acceleration is 0 is, in fact, the 0.60 seconds that we did the second derivative test to the left and to the right. So we already solved for part C. It's the same as having to solve part A and knowing what the time when the acceleration was equal to 0. That was a key piece in solving part A. So part C we just kind of get for free. It's just equal to 0.60 seconds. So I just want to review. We have right now kinematics in one dimension. Don't let the fact that that graph that I showed you, it's 2 dimensions, but we're talking about motion in one direction right now. We're talking about x, one dimension. And we can say that at some time, a particle is at some location in that dimension. We just plug in the time and we know exactly what the x-coordinate is. If we want to think about how that position as a function of time changes over time, then that is x prime, the derivative, which is also the velocity. You could also think of it as you start with a position versus time graph. So position versus time graph would look like this, where you'd have t and you'd have x of t. And so the position versus time graph is also going to have some shape. And at any given point, we can find the slope at that specific point is going to give us the instantaneous velocity, right? The time rate of change of position versus time. And so then we can also think about velocity versus time, and then the slope at a particular point, that's going to be the acceleration. So think of velocity as the slope of a position versus time graph. Acceleration is the slope of a velocity versus time graph. So I had the first derivative of the position as a function of time. That's velocity as a function of time. The second derivative, x double prime, that's the derivative of the velocity, second derivative of the position. That gives us the acceleration as a function of time. I solve for when the acceleration as a function of time is equal to 0. That's the 0.60 seconds. And then what I did is I looked at, okay, well, what is the acceleration both just before 0.60 seconds and just after? And it turns out the acceleration, which again is x double prime, just to the left of 0.60 seconds, it's a negative value. And just to the right of 0.60 seconds, it's a positive value. And so since I know that I'm going from a negative acceleration value to a positive acceleration value at 0.60 seconds, I know that 0.60 seconds is a minima. And so, since you can think of a velocity versus time graph, the slope of that graph is the acceleration. And so, if it's a minima, then we need to realize that this acceleration equals 0 corresponds to when the velocity is its lowest point before it starts to go back up again. And that was this point right here. So that allowed me to say with confidence that at 0.60 seconds, the velocity is at its minimum value. And since we have an expression for velocity, that's x prime, we could just plug that 0.60 seconds into x prime as a function of time, which I showed you. I put the numbers in. I got negative 5.4 meters per second. And again, part C, we get that one for free because we had to figure out when the acceleration was 0 to solve part A. So once again, time equals 0.60 seconds. That's when the acceleration is 0. And I showed you how you could determine if that 0 point corresponds to a maxima or a minima in a velocity versus time graph. So that completes problem number 12. A quick addendum, in case it was a little unclear why I said that if you have a negative acceleration value to the left of 0.6 and a positive to the right, that I know that that's a minima. Let me try and blow up that original graph. And remember that if we plot on our y-axis v of t, and we plot on our x-axis t, then the slope is going to be the acceleration. So think about right here, the slope is 0. Right here, the slope is some negative value. Right here, it's a negative value, but it's less. So you see how it gets less and less and less. It goes to 0. And then here, it becomes positive. If the green continued, it would be more positive here. And so that's what I mean by if the acceleration is negative to the left and positive to the right, that means that it's getting smaller and smaller and 0, and then bigger and bigger and bigger to the right. That's how I know that it's a minima. Now, if instead, so now I'm going to do in blue, if this was positive and this was negative, that would be akin to having a point right here where this is also the acceleration is 0 because the slope is 0. But now, and again, we're doing in blue, it's going to be positive, less positive, 0, negative, more negative. That's what I'm talking about by at acceleration equals 0, looking just to the left and just to the right and seeing what the sign of the acceleration is. And so that's an addendum to kind of further unpack, which is often sometimes called the second derivative test. It tells you at an inflection point whether it's a maxima or a minima. And the key to solving this problem 12 is knowing that the 0.60 seconds, that corresponds to a minima because we wanted to solve for when velocity was at a minimum. This is problem 13 from problem set 1. There will be an exam problem just like this problem. So this problem involves some interstate travel. Let's say that if you can imagine, we have our cardinal directions: north, east, south, and west. And right now we're doing 1D kinematics, just one dimension. So imagine that as we're going along the west to east axis, that's the axis that we're interested in. So we'll say eastbound is positive and westbound is negative. So we've got a couple of different things to consider here. More specifically, we've got reference frames to consider. Reference frames are huge, especially if you ever get a chance to study Einstein's theory of special relativity, which is pretty cool because you come to understand that because of certain properties of reference frames and their relationship to the universe, that time and how much time elapses, and also how much length an object spans, is actually relative. It's actually relative to the motion between reference frames. You can actually have different perceptions of how much time has elapsed or how much an object has, say, contracted based on your different reference frames. Now, we're not going to go there right now, but we are going to think about reference frames. And so more specifically, we are told in this problem that the velocity of u, okay, so this is us. So imagine we're like in a car on the interstate. So I'm going to say the velocity of u, and I'm going to go comma with respect to h, which is the highway. We essentially have three reference frames here. We've got our reference frame, so you can imagine if we're driving in a car, it seems to us like we are stationary and it seems like everything's moving by us. But if you can imagine, relative to, say, the highway thinks it's stationary and we're moving. And so we have to think about what the reference frame is. And so I'm using the nomenclature. The first index, y, is what the reference frame is, velocity of us with respect to h. So the second index is the reference frame. The first index is the object of motion. We are told that the velocity that we are moving with respect to the highway is plus 70 miles per hour. And the reason I put plus 70 is because in the problem we are moving eastbound, and so I say eastbound is positive. So this is the velocity of u with respect to the highway. And so we are asked, if there's a truck, what is its velocity with respect to the highway? And we are told that this truck is in the same lane as we are. It's in front of us. It's also moving eastbound, so it's also moving at a positive velocity. However, relative to us, it seems like it's coming towards us at 20 mph, which is to say the velocity of the truck relative to you. So that's us. I keep saying you and us, but the same thing, right? You imagine we're in a car, there's a truck, and there's a highway. Those are the three reference frames. So the velocity of the truck with respect to us, since it's coming towards us, it feels, even though it's going eastbound and we're going eastbound, it feels like we're stationary and it's going westbound at minus 20 miles per hour. Again, it's actually going eastbound, but relative to us, it feels like it's coming towards us because we're gaining on it. We think we're stationary and we think it's coming towards us. Now, that's not what the highway thinks the truck is doing. And the problem asks us to say, what is the velocity of the truck with respect to the highway? And so here's how you do these relative velocity problems. You have to be careful with the different reference frames. And what you need to do is you have to think of one of the reference frame as being an intermediary. And more specifically, we can do this with indices. If I know that I need to solve for vt comma h, which is the velocity of the truck with respect to the highway, I want my first index to also be truck. The second index for this term is going to be the intermediary. So we have truck, highway. What do we not have yet? Us, right? Or you. So the velocity of the truck with respect to you. You add a second term where now the first index is the y. So you want the two. Can you see how you have the y's as the inner indices? And then the first index is going to correspond to this index, right? You see right here. And then the second index, h, corresponds to the outer. So you want the two inner indices, right, to be the same. That's like the intermediary. And that will allow you to solve for the velocity of the truck with respect to the highway. It's the velocity of the truck with respect to you, but then it's the velocity of you with respect to the highway. We know that the velocity of the truck with respect to us is minus 20 mph. That was this term right here. And we know that the velocity of us with respect to the highway, if you can imagine the highway sees us going by in an eastbound direction, it sees us doing so at 70 miles per hour. And so the velocity of the truck with respect to the highway is 50 miles per hour. This makes sense because even though it's in the same lane and it's going in the same direction, and it is indeed positive, because it's only going 50 miles per hour and we are going 70 miles per hour, we are gaining on this truck. But remember, in your own reference frame, you think you're stationary. And so if you think that you're stationary and you're gaining on something, from your perspective, it feels like it's coming towards you. So you can imagine if you speed up on a car in front of you, it seems like the car is coming towards you. So relative to your reference frame, that truck is going minus 20. It looks like it's going west. But in reality, it's actually going 50 east. It's just going east less rapidly than you are to make you feel like it's going the other direction because you think you're stationary. Let me give you one more example of how you can think about these indices in the reference frames. Let's say that I was interested in solving for the velocity of the truck with respect to you or us. Remember, this problem right here was the velocity of the truck with respect to the highway. Now it's the velocity of the truck with respect to us. So remember, we're going to add two terms. We're going to use one reference frame as an intermediary. And I always want my first index to be the first index that I'm trying to solve for, which is t. But now I want another reference frame as an intermediary that's not y to be the next two indices. And so this is going to be h, velocity of the truck with respect to the highway, plus, can you guess what this first index on this one's going to be? H again. You want the two inner ones to match, velocity of the highway, and the last one I want to match with this one. So this is the velocity of the highway with respect to you. The velocity of the truck with respect to the highway. So the highway is going to be, if you can imagine, it thinks it's stationary. And so it's going eastbound with respect to the highway at 50 miles an hour. Positive. With respect to the highway, the velocity of the truck is 50 mph. That shouldn't be surprising because we just solved for that. All right? And then think about the velocity of the highway with respect to you. We think that we're stationary in our car, even though we're going 70 miles an hour to the east, which would be positive 70 miles an hour. We think we're just sitting there, and we think the highway is going 70 miles an hour to the west. So it would be minus 70 mph. The velocity of the highway with respect to us, we think, is going opposite the velocity that the highway sees us going. And so the velocity of the truck with respect to us is that minus 20 mph I was talking about. Even though it's in the same lane, even though it's going in the same direction, it is going in the same direction eastbound at positive 50. We're going eastbound at positive 70. We're gaining on the truck. In our reference frame, that's the Y, you, us, we think we're stationary and we think the truck is coming towards us. If in our reference frame we're going eastbound, then if it's coming towards us, we think it's going westbound, and that's why it gets the negative sign. So relative to our reference frame, a 50-mile-an-hour truck moving eastbound is minus 20 mph, i.e. it seems like it's going westbound if we're in a car going 70 miles an hour eastbound. So that's how you solve problem number 13.